Hello everyone, and welcome to this IAQ Science Series webinar hosted by the U.S. EPA's Indoor Environments Division. Today's webinar, Estimating the Mortality Burden of Fine Particulate Matter Exposure Attributable to Indoor and Outdoor Microenvironments, will be presented by Dr. Brent Stephens and Dr. Parham Azimi. Please note this presentation reflects the opinions of the speakers and not necessarily those of the U.S. EPA. We're pleased to introduce our speakers and want to thank them both for being here with us today. Dr. Brent Stephens is an associate professor and department chair in the Department of Civil, Architectural, and Environmental Engineering at Illinois Institute of Technology, where he also directs the Built Environment Research Group. He is an expert in residential indoor air quality, or IAQ, and building science, with over 10 years of experience performing residential energy and IAQ field assessments and developing and applying models for energy use, IAQ, and health impacts. He currently serves as the Secretary of the International Society for Indoor Air Quality and Climate, as Research Subcommittee Chair of ASHRAE Technical Committee 2.4 on particulate air contaminants and particulate contaminant removal equipment, and as a member of the editorial boards of the Journal of Exposure Science and Environmental Epidemiology, Indoor Air, and Buildings. Dr. Parham Azimi is a postdoctoral fellow in the Department of Environmental Health at the Harvard T.H. Chan School of Public Health, and was in fact Dr. Stephens' first PhD student. His research focuses on fate, transport, and control of indoor aerosols of indoor and outdoor origin, chronic health impacts of particles, and energy performance of buildings. He currently serves as a member of technical committees, panels, and working groups with ASHRAE, UL Standards, and the American Association for Aerosol Research. Before we start, I'd like to ask Lindsay, who will be helping us with the webinar today, to go over a few housekeeping items.
This work was partially supported by the U.S. Environmental Protection Agency, Office of Radiation and Indoor Air, Indoor Environments Division, the American Society of Heating, Refrigeration, and Air Conditioning Engineers, ASHRAE, through a 2015 New Investigator Award and a grant by EPA's Office of Research and Development to the Illinois Institute of Technology, Assistance Agreement Number 835-75001. The views expressed in this presentation are solely those of the authors and do not necessarily reflect those of EPA or ASHRAE. Thank you, and now to hand it over to Dr. Brent Stephens.
Okay, thank you for that wonderful introduction, and thanks to all of you that have decided to join us for about an hour or so here today on your Thursdays in the middle of a work week. As we get started, that was a nice introduction here. We're going to kind of split this talk. I'll give the first half or so, and then I'll transfer it over to my colleague Parham Azimi, who, as you heard, was actually my first PhD student and then postdoc with me for a little while, and now has moved on as a postdoc in the Healthy Buildings programs at the Harvard School of Public Health. And this work is sort of a culmination of maybe 3 or 4 years of work that we've worked on together to try to estimate the mortality burden of fine particulate matter exposure that's attributable to exposures in different microenvironments and where we spend most of our time. And before we go on, I do want to acknowledge a few individuals. There's really more that have helped us with this work than are listed here, but a key individual is Laura Call, the EPA, who really spearheaded this back at a National Academy of Sciences workshop on indoor PM in 2016. We had a discussion about what's out there, what can we sort of learn about indoor and outdoor sources of particulate matter, their likely association with health effects, and where are we actually exposed to particulate matter. And so she really made all this work happen, and she also brought a team along with her, including Lou Harriman and Terry Brennan, who are consultants that work with EPA and other organizations. They really helped shape kind of the way we've thought about this work throughout time. And then Vito Alacqua, also at the EPA and the Indoor Environments Division, has really helped us on the technical side of a lot of this work, and a number of other folks have helped as well. And so as we get into this, I am going to begin with kind of a brief introduction or sort of a refresher on what we know and don't know about particulate matter exposure and human health. And so if you're relatively new to this arena, the basic idea is that particles exist in indoor and outdoor environments all across the world, anywhere you go. Particles are suspended in air. They're mixtures of solid and liquid particles with a wide variety of constituents and sizes. This is an image here of just a few representative types of aerosols, like soot from engine exhausts or biomass smoke from wildfires or cooking and that sort of thing, dust particles, sea salt, and other marine organic type particles. even allergens like pollen and so on and so forth. So a wide variety of sizes and shapes and constituents exist in any environment in which we spend our time. What's also important to know is that while there are many outdoor sources of particles, there are also many indoor sources of particles. Outdoor aerosols have been studied for a very long time. We understand that there are numerous traffic-related sources of particles in ambient environments. There's industrial sources of particles from energy conversion. There's natural sources of particles from marine environments, from wildfire smoke, and many others. And there's also secondary particles that are generated through atmospheric reactions. So in any environment, you sample particulate matter in the outdoor environment, and you'll find contributions from any number one of these and others. And we also have learned over the last few decades that there are a number of indoor sources of particles. This is a snapshot from this National Academy of Sciences workshop summary on indoor PM and health risks. This sort of infographic below. Some of the most common indoor sources of particles, for example, include appliances, so things like desktop laser printers and even 3D printers. Even cleaning activities generate particles that aerosolize or emitted into the air, things like dusting, vacuuming, and ironing, among other activities. Of course, combustion, including emissions from food as it's cooking, emissions from gas stoves as they're operating, also emissions from electric stoves as they're operating and heating food, that will generate particles, not through combustion, but through other processes. And of course, cigarettes and e-cigarettes and that sort of thing, although we're not talking much about environmental tobacco smoke today, that's sort of a whole other thing. We're exclusively sort of avoiding that or limiting that. Particles are also formed in indoor environments through chemical reactions between various compounds. And we also emit particles through resuspension. So when we walk on the floor, we walk on carpets or hardwood, we'll kick up particles into the air. And there are numerous other indoor sources. And I mentioned a wide range of sizes and composition. In any indoor and outdoor environment, you'll have particles that range from as small as a few nanometers to as large as tens of micrometers or so. And size is really important for a number of reasons. First and foremost, because size governs deposition in the respiratory tract. So for example, some smaller particles, sort of under 100 nanometers and maybe even smaller than that, tend to penetrate into the deeper regions of our respiratory system. So smaller particles can penetrate past our head airways and enter, for example, the alveolar region in our lungs where gas exchange occurs with the blood. And that is sort of thought to be or understood to be an important way that particles enter our bloodstream and enter our bodies to generate or cause the health effects that we see in epidemiology of studies and so forth. And so in terms of size, one thing that's important to note is that most particles of outdoor origin are much smaller than 100 nanometers, really, everything in this shaded green area. And generally the same is true for indoor particles, at least on a number basis. So small particles exist everywhere is essentially the story. And we measure and classify particles based on a wide range of sort of measurement methods and metrics that we use. I've already mentioned these small particles, less than 100 nanometers. We usually refer to those as ultrafine particles. But then you're also probably more familiar with PM2.5 and PM10, which is the mass of particles smaller than 2.5 micrometers in diameter and 10 micrometers in diameter. These are regulated in the United States as part of the National Ambient Air Quality Standards. So we measure these all over the United States and elsewhere in ambient environments. And we're mostly concerned with PM2.5 because the epidemiology evidence, as I'll show you in a bit, has been shown to be quite strong with PM2.5. And also PM2.5 includes these smaller particles that can penetrate past our head airways and enter our lower respiratory system. And so just to give you one sense of the scale of the things that we're talking about here, if you're not familiar with this is a graphic that was included in the EPA's recently updated guidance documents on using air cleaners and air filters in homes. There's a link here at the bottom of this. And so if you imagine like a fine grain of sand on the beach, it's on the order of 100 micrometers or so. We can see it, but it's really small. And then if you go a little smaller than that, you can imagine the sort of narrow dimension or the width of a human hair is about 50 or 70 micrometers. We can still see it, but it's really, really small. And then about five or seven times smaller than that, you've got 10 PM10, or particles that are smaller than 10 micrometers in diameter. And then another fourth-fold smaller than that is PM2.5. So we're really talking about today PM2.5, which is everything that makes up this small little red speck relative to this fine, blown-up version of a particle of beach sand. And what we have sort of gathered is that we know a whole lot about the health effects associated with outdoor PM sources, and we know a whole lot less about indoor PM sources. And most of what we know about outdoor PM sources and health effects really is attributable to PM2.5. And so let's look at some of the evidence here that we have. So we gain a lot of this evidence for health effects through epidemiology studies. And so here's just an example of a few key studies. There are numerous others over the last several years that have used large epidemiology cohort studies to sort of characterize the risk of adverse health effects. In this case, we're mostly focused on mortality associated with ambient or outdoor PM2.5 concentrations. So you can, if you're not familiar with this sort of body of work, this is just an example of several studies where you essentially take outdoor PM2.5 concentrations, whether they're measured or modeled or both, across a region that you're looking at, and then that becomes essentially the x-axis on a graph like this. And then you develop these models where you sort of fit a model to the observed mortality increases that you see that are correlated or associated with changes in outdoor PM2.5 concentrations or changes in outdoor PM2.5 concentrations in those areas. And so, for example, whether it's back to the Harvard Six Cities study, where there was after controlling for a number of factors, a number of confounding variables and that sort of thing, this relationship comes out where you can sort of characterize the increased mortality risk as a function of outdoor PM2.5 concentrations. That's true for a large ACS, American Cancer Society cohort, for lung cancer, cardiopulmonary mortality, and then overall all-cause mortality. And you can see there's scatter in all of these studies, but essentially what you can do is we've got enough information that you can develop concentration response or, say, exposure response functions where you can characterize through the shape of this curve and sort of the slope of the curve essentially how toxic or how potent outdoor PM2.5 is for leading to excess mortality in a population after you've controlled for a whole bunch of other variables. In fact, we know enough that about 10 years ago, there was an article in the New England Journal of Medicine that tracked changes in life expectancy over time, as life expectancy in different areas across the U.S. has improved from the 80s to the 90s, for example. At the same time, outdoor PM2.5 concentrations decreased from the 80s to the 90s and to the 2000s. In fact, we keep doing better there. We keep getting outdoor environment in the U.S. cleaner on average. And through this association, again, there's lots of scatter and there's lots of other reasons that explain this, but essentially there was a significant correlation where if you could imagine you reduce outdoor PM2.5 by 10 micrograms per cubic meter, there's on average an increase in life expectancy of a little more than a half a year. So this study built on this epidemiology evidence to show that if you reduce outdoor PM2.5 concentrations, one would expect an increase in life expectancy. In fact, there's been so many, outdoor PM2.5 and mortality specifically, but other endpoints as well, other health endpoints as well. There's been so many of these epidemiology studies that researchers can do what are called meta-analyses, where you take the effect estimates, or essentially the slope of that curve that we talked about for associations between elevated mortality risk or mortality or death rates in a location and local or nearby ambient PM2.5 concentrations. You take those risk estimates and you can pull them together. And for example, researchers from EPA in 2016 published this meta-analysis where they kind of came up with this pooled estimate. So you can weight each study by a number of factors and kind of say, okay, look, we know there's scatter in this sort of data, but just how sort of toxic, if you will, is outdoor PM2.5 or in the epidemiology studies, what is the relative risk per an increase of 10 micrograms per cubic meter in PM2.5 concentrations outdoors that we're seeing? And they come up with an average here, kind of shown with this line and then a shaded area to capture some uncertainty. And a typical concentration response effect estimate for PM2.5 and mortality in mostly U.S. studies, although I think there's a few European studies as well in here, is on the order of about 7% increase in mortality for 10 microgram per cubic meter long-term average, like annual average, increase in outdoor PM2.5 concentrations. So again, we know a lot about outdoor PM and mortality, and we know a lot of that through these large epidemiology studies. And then we also have had sort of enough experience with this that what we can do is take epidemiology studies and then generate models to try to more expansively predict or estimate the mortality burden of ambient PM2.5 exposure across the U.S. or any other region. And so, for example, we have this large network of ambient monitoring sites where we've got hundreds of counties with regulatory monitors measuring PM2.5, every hour, every day, every year, and summing that information up. And so we have measurements across the country, mostly where people live. And then we also have atmospheric physics and chemistry models that you can use to kind of fill in the gaps for those spaces where there aren't monitors, and you can get an idea of PM2.5 concentrations across the United States in different areas. And then if you combine those with what we mentioned were concentration response functions, where you can use a variety of different model forms and shapes and so forth, and also effect estimates from the literature, essentially the slope of this line is the way to think about it. And then you can sort of predict or estimate the relative risk or the increase in mortality, for example, in an area based on its ambient PM2.5 concentration. And so an example of how this is utilized is a study here in 2012 that combined these sort of measurements and models of outdoor PM2.5 concentrations in different counties, all the counties across the U.S. essentially, looked at the underlying mortality rates in those areas, and then used some assumptions for the average outdoor PM2.5 toxicity or like effect estimate captured here in this beta. Again, it's kind of like the slope of that relationship between concentration and response. And then you can calculate based on the ambient PM2.5 concentrations, what's the likely mortality associated, or what's the mortality burden attributable to outdoor PM2.5 across the United States. And by doing this, and using data for the year 2005, for example, researchers at EPA in 2012 estimated that about 130,000 deaths in the United States were attributed to outdoor PM2.5 exposure. And there's actually been a number of studies that have tried this sort of thing using a variety of approaches where you're linking epidemiology studies with models, both air quality models and measurements, and then these concentration or exposure response models to estimate the mortality burden associated with exposure to outdoor PM2.5, both in the United States and globally. So I mentioned this first reference here. This is just a snapshot of recent efforts here. There's a few more that are out there, but these are highly relevant to our work. I mentioned this first reference in 2012, who used basically this very typical log linear function to calculate a change in mortality as a function of the underlying exposure, the size of the population, the mortality rates in the area, and then this beta, this effect estimate, this slope between the relationship of mortality risk and outdoor PM2.5. And so they used this with in 2005 for using population and pollution data for 2005, and like I said, estimated about 130,000 deaths in the U.S. were attributable to outdoor PM2.5. You should note also in the parentheses here is confidence intervals. This is a highly uncertain sort of science, and so they actually have a pretty wide confidence interval band because there's uncertainty in the effect estimate and a number of other factors. So from maybe 50 to 200,000 deaths or so. They actually provided another estimate with like a stronger potency factor, a bigger slope, a bigger beta value of maybe could be as high as on the order of 300,000 deaths per year that are attributable to ambient PM2.5 exposures in 2005. The real number is almost impossible to actually tell, but these are ways to kind of get at it. And so a few years later, this same group published a paper, Environmental Health Perspectives, using essentially the same model form, but using updated population and pollution data in 2010, and estimated mortality burden associated with ambient PM2.5 in the U.S. was around 120,000 using one model estimate, and then maybe around 200,000 using another kind of risk factor or another sort of slope, if you will. And so again, kind of bouncing around those same numbers as before. Now, more recently, in 2017, Cohen et al. Published a paper using what's called the Global Burden of Disease Integrated Exposure Response Function. Published this in The Lancet to calculate or to estimate mortality risks associated with PM2.5, outdoor PM2.5 exposures across the world, including the United States. Basically, it's a very similar function. Sorry for putting some of these equations on, but it's important for kind of telling our story. It's a very similar function as before, but with some modifications and a few different parameters, and fit to a wider variety of PM2.5 concentrations and just a couple of core health impacts or different types of health outcomes related to mortality. And so they came up with an estimate of about 88,000 deaths were attributable to ambient PM2.5 exposure in the year 2015, with a confidence interval from, say, 67 to 115K or so. So a little bit lower than some of these other estimates, and there's a few reasons for that. And then most recently, just last year, in the Proceedings of the National Academy of Sciences, Burnett et al. Published like a modified or a new global exposure mortality model. Again, somewhat similar sort of form, but again with some different factors, and takes into account a few other things and fits the model through yet another kind of set of historical epidemiology studies. And then they apply this to the year 2015 to the United States and Canada. We couldn't find just the United States alone, but of those two countries, the U.S. makes up about 90% of the population, so you can imagine these are pretty close to U.S. only, or maybe subtract 15 or 10% or so. And they estimated somewhere between 120 and 210 or so thousand deaths associated with ambient PM2.5 exposure in U.S. and Canada, which is a little bit higher than the previous study. And then finally, there was another study just this year, Tessum et al., and again in the Proceedings of the National Academy of Sciences, who used sort of a modified global burden of disease model and estimated about 130,000 deaths attributable to ambient PM2.5 exposure in the U.S. in 2015. And so this is just kind of a body of what's out there where researchers have taken what's known from epidemiology cohorts and then applied them to models using these health impact functions or risk functions, a variety of sort of shapes and magnitude of facts, but we kind of get some similar ballpark figures sort of suggesting that the ambient PM2.5 burden or mortality burden in the U.S. is likely on the order of, say, 90 to 200,000 deaths per year, maybe somewhere in between that. And so that is all about ambient PM2.5. This is all done assuming that you can measure outdoor PM2.5 concentrations, and that those are a reasonable surrogate for people's exposure to PM2.5. But the question is, where are we really exposed to PM2.5? And a really important point here is that nearly all outdoor air pollution epidemiology studies just don't account for an important point, and that is that we spend most of our time indoors. Maybe you've heard it before, we spend almost 90% of our time indoors on average. You'll find that on the EPA's website and other places. You know, that comes from studies like the National Human Activity Pattern Survey that surveyed almost 10,000 people a little over 20 years ago now. The data haven't changed a whole lot, but basically they called people and asked them what they did yesterday, you know? And when they tallied all the numbers, it turns out that on average, people spend about 87% of their time indoors, and the vast majority of that they spend inside a residence, almost 70% of your time at home, followed by about 11% in other types of buildings, and then only 7 or 8% outdoors on average. Of course, this will vary, you know, from season to season, from person to person, from day to day, but this is a pretty robust snapshot of how we spend our time. And so where are we exposed to PM2.5? This question actually just came up. I've got a screenshot of a tweet from Joe Allen, who's a professor at the Harvard School of Public Health and who's actually Parham's boss as of about a couple months ago. And so here he is quoting Marina Vance, who's a professor at University of Colorado Boulder who studies indoor air and other things. And she was recently quoted in this New Yorker article on the hidden air pollution in our homes. The New Yorker article is a really nice piece if you haven't read it, talking about how outdoor air has been regulated for decades, but emissions from daily domestic activities could be more dangerous than people really imagine. And so Joe quotes Marina here saying, there's a big question here. This is in this article. If all these studies have found an association between outdoor air pollution and a decrease in life quality and life expectancy, but we're not outside, how does this relationship still hold? And after a little Twitter discussion, Joe Allen here, I'll quote, says, exactly, this is the dirty secret of outdoor air pollution, or more accurately, the dirty secret of outdoor air pollution epidemiology. I'm not so sure it's really a dirty secret or that much because it can be really challenging. I think a lot of epidemiologists understand this, that you sort of have to use these outdoor concentrations as surrogates for exposure because we can measure those in hundreds of places. Whereas if you're going to do a cohort study with 1 million people, you might have to measure indoor concentrations in 1 million people's homes. Like the scale of that is really amazing to try to do and resource intensive. But moving along these lines, I also include a quote here from a workshop summary that I mentioned before from the National Academy of Sciences workshop on indoor PM, the health risk of indoor exposure to PM, where Charlie Weschler is paraphrased here, who's a researcher who's worked in indoor air for many years, and he said that he would argue that since the bulk of our exposure to outdoor PM actually occurs indoors where we spend most of our time, more is probably known about the risk of indoor exposure to outdoor particles than what is known about the risk of outdoor exposure to outdoor particles, or for that matter, for indoor exposure to particles of indoor origin. And the point is, that's probably true, but we haven't really quantified that very well at this point. And so that leads us into our work here. That's kind of an overall picture of where we're at. And so we've been working over the last few years to try to attribute exposures to PM2.5 of indoor and outdoor sources to the different environments where we spend most of our time. So I'm going to start with a conceptual framework of this model, because we sort of developed a framework and then we apply it. And so let's start with a couple of key definitions if you're not that familiar with this field. If you go in and you measure particles in any microenvironment or in any environment, whether it's a vehicle, an office building, or in this case, a home, if you measure indoor particles and you measure outdoor particles at the same time, you'll come up with the indoor-outdoor ratio, a very simple number that tells you the ratio between inside and outside particles. And what will happen there is that the indoor particles are a function of outdoor particles that enter through open windows, that enter through any mechanical ventilation, and that enter through infiltration, through cracks and gaps in the building envelope. All right, so indoor particles is kind of a complex mixture of outdoor particles that come indoors and particles that are emitted indoors. And it can be tricky to separate through measurements alone what's coming from indoors and what's coming from outdoors. That's something that my research group is focused on and a number of others. And then if you go in a home and you measure indoor particles when there are no indoor sources, or if you measure like a chemical tracer of PM2.5, for example, for which there are no indoor sources, but there are outdoor sources, you can come up with an estimate of what's called the infiltration factor. So this is a number between 0 and 1 that basically tells you how much the building protects from outdoor PM, or in other words, how much of outdoor PM infiltrates and persists inside buildings or inside any microenvironment. And so if you look at the literature of who's measured indoor and outdoor PM ratios for different classes of particles across the world, you'll find a great paper that was published in 2011 by researchers at Tsinghua University in China that first reported on these big studies that have measured indoor and outdoor ratios for PM10, some other particle metrics, and then the one we're focused on today, PM2.5. And so this is the average, each bar is the average of a study of a number of homes. And so the line here is 1 marked here. You can see some studies in some homes found pretty low indoor-outdoor ratios, meaning indoor sources probably aren't very big. And then some studies found really high indoor-outdoor ratios, meaning indoor sources are really big because you've got more particles indoors than outdoors. And on average, if you need a number to just tell somebody what the average indoor-outdoor ratio for PM2.5 is in a home, it's about 1. But that's a complex mix of indoor and outdoor sources that kind of commingle together. And if you look at in the same review article, they also surveyed a number of studies, there are fewer studies, but a number of studies that measured PM infiltration factors. So this tells you the indoor proportion of outdoor particles, again, in homes. So the bars here are the average across a large study, and the number of homes included in each study is included here in the parentheses. PM10 is included over here, and again, we're focusing on PM2.5. The gray bars are U.S. homes, and then a few white bars are European homes. So if you look across this, there's variability among studies and of course, variability among homes. These are just the averages of each study. But the median infiltration factor for PM2.5 across homes is somewhere around 50 or 60%, meaning that your indoor exposures to outdoor PM2.5 in your home are probably, on average, about 60% or 50% of what they would be if you were standing right outside. That's because the building envelope filters some of the particles. Particles enter and deposit on surfaces, and then they're controlled by any filtration systems that you might have in a building. So with that kind of background, thinking about indoor-outdoor ratios, infiltration factors, and indoor and outdoor sources, this brings up this key issue again. So I want to kind of reiterate here. What we showed earlier was these historical epidemiology associations between ambient PM2.5 concentrations and adverse health effects, such as mortality, which is what we're focusing on here. Those have inherently, or maybe we could say inadvertently, accounted for exposures to PM2.5 of outdoor origin in all of the different microenvironments or environments in which we spend our time. Plus, we're exposed to numerous indoor sources of PM2.5 in those environments. So with this work, our goal was to develop and then apply a framework for estimating the total U.S. mortality burden attributable to PM2.5 exposure, accounting for both indoor and outdoor sources in the primary non-smoking environments where we spend most of our time. And the framework combines a typical exposure response function, like we showed earlier, with what we call adjusted mortality effect estimates. They basically take those concentration response effect estimates for PM2.5 and mortality associations and modify them to account for the underlying exposures to PM2.5 of outdoor origin that likely occurred in the original epidemiology populations from which those effect estimates were derived. So that's the first part of this that Parham will talk about starting on the next slide. And then he'll also talk about how we demonstrated the framework using a few different scenarios or a few different case studies to try to estimate the potential magnitude and bounds of the U.S. mortality burden attributable to total PM2.5 exposure, accounting again for both indoor and outdoor sources across all these non-smoking environments that we spend our time in, and using a variety of what we think are reasonably realistic assumptions. And so this work was published late last year in the Journal of Exposure Science and Environmental Epidemiology. You can download it through this link here for free if you'd like to learn more details. And so with that, I'm going to turn the controls over to my colleague Parham Azimi, who will take you through some of the methods and results, and then I'll join back in the end.
Thank you so much, Brent, and hello, everyone. This is Parham. Thank you for joining us in this webinar. I'm so glad that I'm here today to present our study in collaboration with EPA. So, as Brent mentioned, our estimates, we need a better estimates for mortality effects of PM2.5. To make it clear why we need these estimates, let me to give you an example. For example, in Pope et al. 2002 study, they reported a 6% increase in all-cause mortality-related risk with 10 microgram per meter cube increase in outdoor PM2.5 concentration. But the question here is, does the average human exposure concentration to PM2.5 of outdoor origin actually increase 10 microgram if outdoor PM2.5 increases 10 microgram per meter cube? With the introduction that Brent told us, and we as indoor scientists, we know that the answer is no. People are actually exposed to a fraction of outdoor PM2.5 depending on their activity patterns. So this number should be something less than 10 microgram per meter cube. So that's why we think we shouldn't use the relative risk results directly from epidemiology studies to estimate all-cause mortality associated with indoor exposures. By saying that, let's look at regular concentration response function that it is used in many studies, that some of them was shown in previous slides. We got this function and we modify it. We modify it in such a way that we can consider different microenvironments and also different particles from different sources. So in this equation, the z-index is actually showing the parameters which are related to indoor or ambient generated particles. And J indexes are actually showing the model parameters which are associated or related to the different microenvironments. So at the beginning, we're going to focus on particles from generated in indoor or outdoor, and then we're going to talk about different microenvironments. So here, let's expand that part which was related to the Z-index part. In this part, we say that we can estimate the total mortality associated with PM2.5 by multiplying beta value times to the exposure that we are exposure of PM2.5 of indoor generated particles and outdoor generated particles. If you wanted to describe it simply, it is showing how much toxic are PM2.5. So it could be different from indoor generated particle and it could be different for outdoor generated particles. So this some of the studies were showing that ambient origin PM are more harmful than indoor generated PM. But the other studies was showing that indoor generated particles are as toxic as outdoor PM if they are not more toxic. So that's why we had to make this like a key assumption. We made this key assumption in our framework that we assume both indoor and outdoor origin particles have similar toxicity or similar beta value. This is a key assumption. We know about that. But the framework that we are developing here, it can handle other assumptions if it is needed. Now let's go back to this equation. For the first part, how we get this beta value and how we modify it. At the beginning, we're gonna tell you how we got this beta value from epidemiology study. For that, we rely on a recent meta-analysis by Fan et al. 2016 that they were estimated the beta value of particles of outdoor origin is about 7.3% per 10 microgram per meter cube. This their meta-analysis was shown here in Brent slide number 11, how they gather the existing epidemiology studies and they by doing a meta-analysis they got this like a approximate estimate of what is the PM2.5 mortality. We got that number for relative risk. And then from that, we got the beta value using that equation that you can see here, using this equation. And then we find the beta value for outdoor origin particles equal to 0.007 per 1 microgram per meter cube. And this was the same value that we used for indoor generated particles as well. And then when we got this number, now we want to modify it. To modify this number, we consider different microenvironments and the infiltration factor of PM2.5 to those microenvironments. In this framework, we consider 4 main microenvironments, including inside residences, inside other buildings, inside vehicles, and outside. All of these studies was based on Captions et al. 2001 study that Brent talked about them before as well. And in the next few slides, I'm going to tell you about the distribution of the time that we spend in different microenvironments and also the assumptions that we use for the infiltration factors. And after that, we apply it to this equation on the top, and we modified beta value for PM2.5 that it can be used for indoor exposures as well. Okay, so let's start with inside residences. For inside residences, the average time that we spent in residences was about 68.7%, with the distribution that you can see on the bottom left side graph. It is reported in Captions 2001 study. And then the infiltration factor was based on the infiltration PM2.5 infiltration factors reported by Chen and Zhao in 2011 for U.S. buildings. So we talked about this study before as well. After we got this infiltration factor, we fit a beta distribution to these numbers to be able to have a good idea of how this infiltration factor would be or what is the range of them. And then for inside vehicles, the bottom left side is showing the distribution of the time that we spend in vehicles which was on average 5.5%. And for in the filtration factor, we rely on a study in 2013 from Huda and Freund. So in that study, they estimated the PM2.5 infiltration factor for two scenarios. One scenario was when the recirculated air was the car had a recirculated air, and then the second scenario was when the car had outdoor air ventilation. By combining these two scenarios, they come up with an infiltration factor equal to 0.43 for cars. So that we use these numbers as the average of the two scenarios for cars and how people are exposed to PM2.5 in these two scenarios. And next step was for outdoors exposures. Again, Leptis et al. 2001 reported a distribution for the time that you spend outdoor, and on average, this number was about 7.6%, and infiltration factor was obviously 1 for PM2.5. After we got the time that we spent in the previous three macro environments, we estimated the time that we spent in other buildings than residences by subtracting the fraction of the time that we spent in the other three macro environments from 1. And the average time is come up to be 18.2% for other indoor locations like at offices, factories, bars, schools, or restaurants. The infiltration factor for these buildings was based on a study from Ben David et al. In 2017, which they suggested the infiltration factor of PM2.5 for offices is about 0.49. That study was happening in Finland and for office buildings, but because of the lack of data, we used this study for all of other buildings than residences to estimate the infiltration factor of PM2.5 to them. So when we got all of these results, we can find that modification factor, which was a sigma or sum of the time that we spend in different microenvironments times the infiltration factor of PM2.5, and that modification factor was 0.6. So our modified beta value for exposure to PM2.5 of both outdoor and indoor origin, it came up to be 0.16 per 10 microgram per meter cube, and that was the number that we used in this study. So now let's go and talk about the second part of the, or expand the second part of the modified function that we are using in this framework. In the second part, we wanted to know what is the concentration of PM2.5 in different microenvironments, and actually the changes of the concentration in comparison of the threshold, so delta C. So for to estimate the concentration, we divided our particles to two main types, indoor generated and ambient generated particles. We assume that we are exposed to indoor generated particles in residences and also other buildings or indoor indoor environments, while we are exposed to ambient generated particles in all four main macro environments. So in this framework, we assume that we are not exposed to indoor generated particles in outdoors and also inside vehicles. To estimate the concentration of PM2.5 of indoor and outdoor origin in these four main macro environments, we make some assumptions and gather some distributions that we are going to talk about them right now. All right, so let's start with outdoor PM2.5 concentration. So for that, we rely on an EPA nationwide monitoring network data for 2012, in which they reported an average of 9.1 microgram per meter cube for PM2.5 concentration in 2012 in the whole United States. And we fit a log normal distribution to that data with the 10th and 90th percentiles of 6.6 and 11.2 microgram per meter cube. That was the concentration of PM2.5 outside. For the concentration of PM2.5 inside residences of both indoor and outdoor origin, we considered two scenarios. Okay. In the first scenario, we relied on two big field studies for residences. We chose these two studies because these two studies consider or measured and reported the PM2.5 concentration inside and outside, and also infiltration factor of PM2.5 in the residences simultaneously. So by knowing these three parameters, we could estimate concentration of PM2.5 of indoor origin inside residences, or C in. So the first study was RIOPA study, which was considered they measured 212 non-smoking residences in 3 United States cities, and the other one was MESA Air, which they measured these parameters in more than 200 homes in 7 U.S. cities. Our first combination in scenario 1 was RIOPA only. In that scenario, the C in was 9.5 microgram per meter cube. Then the second combination was MESA Air, in which the C in was 2.8 microgram per meter cube, the average C in. And finally, our primary combination, our primary scenario in scenario 1 was a 50-50% combination of RIOPA and MESA study, and the mean C in the primary combination or scenario was 6.1 microgram per meter cube. So now we know that what is the concentration of PM2.5 of indoor origin inside residences. So now we wanted to know what is the concentration of PM2.5 inside residences, the ones that are coming from outdoor. So for that, we need to know the infiltration factor. So the infiltration factor for these homes was coming again from the RIOPA and MESA Air studies. We talked about these studies again before, but the infiltration factor in RIOPA studies was 0.54, and in MESA Air study was 0.6. And the distribution that they were using for infiltration factor is showing in this figure on the left side. So that was our first scenario. In the second scenario, we rely on a regional model output, which was coming from a nationally representative set of combined residential energy and indoor air quality models for non-smoking residences in the United States. This research was done by Illinois Tech group last year, and it was an interesting study because in that study, they considered a total of almost 4,000 individual home models in 19 United States cities. These models represented of about 80% of the whole United States housing stock. And they were reporting the indoor concentration of PM2.5, indoor and outdoor ratio, and also infiltration factor for different regions in the United States. And they come up with a population-weighted average of indoor PM2.5 of indoor origin equal to 5.9 microgram per meter cube. This number is actually very close to that our primary combination assumption for PM2.5, which was a combination of MESA and RIOPA, which was 6.1 microgram per meter cube. So both of these assumptions was kind of very close to each other. Because we know that the infiltration factor, we could come up with both C in and C in out. C in out is a concentration of PM2.5 inside residences from outdoor origin and particles. For non-residential building, for both scenarios, we rely on a study from Hani et al. In 2005. They were suggesting a log normal distribution for indoor PM2.5 of indoor origin with a mean and a standard value of 4.18 and almost 5 microgram per meter cube respectively. For vehicles in both scenarios, we assume that there is no sources of PM2.5 inside a vehicle. Again, for the infiltration factors, for other environments, we consider Ben and David 2017 data, which was an average of 0.49 for infiltration factor of PM2.5, and inside vehicles, as we talk about that, the infiltration factor of PM2.5 was 3, which was a combination of two scenarios for air conditioning system of the vehicle. And the distribution of both of these infiltration factors are shown in the graph here in this slide. So now we know the concentration, so we have to find the threshold. The threshold to find the delta C, or the concentration which we are exposed to it more than the threshold. In this study, we consider a threshold of 0 for all of the environment. It was based on some of the recent studies that they were suggesting that even a smallest amount of PM2.5 or a smallest concentration of PM2.5 still have some health impact on people. So that's why we consider a threshold of 0 for PM2.5. But the other studies was consider different numbers for threshold of PM2.5. For example, Fan et al., they consider 1 microgram per meter cube for PM2.5 threshold. Why, again, Fan et al. In 2017, they consider 0. Cohen et al. In 2017 consider uniform distribution for PM2.5 threshold between 2.4 and 5.9. Burnett consider 2.4, and also Tessum consider a threshold of 5 or 8 microgram per meter cube. So that number was different, but again, our model can handle any changes in the assumption. So if we come up with another threshold, we can easily apply it to the framework that we are presenting here. So finally, there are two parameters in our modified CR function, was annual baseline mortality rate and population over 35 years old. So why we are considering population over 35 years old? Because this is the population that most of the mortality associated with PM2.5 exposures happening in this range. And lots of the studies are showing that actually mortality happening for over than 35 years old. So we just consider that, and we consider the annual baseline mortality related to this age group in 2012 in the United States. This data was coming from census data in different United States divisions. So we consider all of these divisions, including New England, Middle Atlantic, and so on till Pacific divisions, and we end up with population weighted nationwide numbers for these parameters, including annual baseline mortality and population over 35. So the nationwide population weighted estimate was using in the first scenario, and for the second scenario, we were using these regional basis data in our framework. So when we gathered all of this data, so this data that we gathered from all of the sources, they had a distribution. So we had the opportunity to apply a Monte Carlo simulation to this data. So we use a Monte Carlo simulation with 10,000 iterations to sample from the distributions of each model input parameters. So we have to say that each iteration that we are presenting is actually representative of one estimate of total PM2.5 mortality burden associated with both indoor and outdoor origin in all macro environments. When we demonstrate these results or these 10,000 estimates of total PM2.5 mortality in a histogram, we could fit log normal curves to these numbers, as you can see it here. So these log normal curves could be fitted to these results. And for our first scenario, we showed that the median, our median number or our best estimate for RIOPA-only study in a RIOPA-only case was about 300,000 deaths in 2012. For meta-only scenario, it was 230,000 deaths. And for our primary combination, or for our primary scenario in scenario number 1, our best estimate of total PM2.5 mortality was almost 256,000 deaths in the United States in 2012. that was for scenario 1, which was a nationwide scenario, which we were using 2 field studies. In the second scenario, which was basically a regional analysis on a mortality rate, we tried to come up with some results for the regional basis. We have to say that, we have to emphasize that the original mortality analysis had even more limitations than our nationwide method or estimate, because lots of these parameters that we used in this model was not available in regional basis. So, for example, in regional mortality analysis, we didn't consider different time activity patterns or potential difference in toxicities, but still, we think that this analysis would give us some idea about what region of United States would face a higher burden of PM2.5 mortality associated with PM2.5, which was the South Atlantic with more than 56,000 deaths in a year in 2012, in comparison of, for example, New England, where we just had 14,000 deaths based on our estimates. That is a total mortality. And now if we wanted to see what is the risk of mortality for people, so we divided this mortality to the number of the population, and we come up with a new factor, which was like a mortality rate per 100,000 population in different census divisions. And in this one, we were showing that people who are living in East South Central would have a higher risk of mortality associated with PM2.5, with 116 deaths in each 100,000 population, in comparison of people who are living in a mountain area with just 71 deaths for each 100,000 population. So, as I said, this regional analysis has so many limitations, but it will give us some kind of idea that what parts of United States are faced with a more burden of PM2.5 mortality. By saying that, I'm going to let my colleague Brent to discuss the results in more details and also talk about our limitations in more details from here. Thank you.
Okay, thank you, Parham, for doing all of that heavy lifting. So I'll wrap it up with a few slides here to kind of put this in some perspective. I just want to show the results across all of these scenarios that we applied the framework to in kind of a different way. So this shows our sort of best estimates of the mortality, the total mortality in deaths per year associated with each or predicted through each one of these sort of two scenarios and sub-scenarios across the U.S. And then it's organized here by the darker blue bars, the bottom two darker blue bars for each scenario are indoor origin sources, or those that mortality attributed to indoor sources in different microenvironments. And then the lighter blue and gray bars are those attributable to outdoor sources. And so I'm going to highlight scenario 1, RIOPA/MESA. As Parham explained, scenario 1, MESA only basically assumes that we can it basically assumes that measurements from over 200 homes in 7 cities in an older population in the MESA Air study, which was one of the few big field studies that used some methods to determine how much indoor PM came from indoor sources and how much came from outdoor sources. Scenario 1, MESA only, assumes that cohort is basically, reasonably representative of the whole U.S., which is probably not true. And the same goes for RIOPA only. It makes that same sort of assumption, which is also probably not true. These are just 3 cities and 200 plus homes. So if we assume that across those we could sample equally and do the combined RIOPA-MESA scenario, this is probably our best estimate as of today of these microenvironments and indoor sources and their contribution to total mortality. So if we look at this is the kind of total mortality estimate of about 255,000 deaths, with 160,000, or about 60% or so, attributable to outdoor sources, with the biggest contributor being outdoor sources inside homes, where we spend most of our time, actually followed by outdoor origin inside other indoor environments. And you can see outdoor origin in outdoor environments is this small sliver up here. And then there's a sort of, compared to the regional scenario 2, there is a lower indoor burden because we assume through these field samples that this represents the average indoor proportional exposure. But still, if we work with all those assumptions that Parham outlined, we estimate somewhere on the order of a little under 100,000 deaths might be attributable to indoor sources, mostly in homes, but then also in other office-type environments and restaurants and that sort of thing. Again, there's a lot of uncertainty, but these are ballpark estimates that we're trying to make using this framework. And then if we move over to scenario 2, the regional model, we get a little bit higher contribution to total mortality, estimating around 280,000 deaths per year, with about 139,000 coming from outdoor sources, and a larger portion, 140,000, coming from indoor sources in these different microenvironments. Mostly because this scenario assumes a little bit larger indoor sources through the model that we used. We're not really even sure which one is right. We're just trying to make some good estimates, and then there's also a number of limitations to this, as I'll talk about in a couple of slides. And so regardless of the magnitude of the mortality estimates, one really key outcome of this work is that we can actually average across all of these scenarios and get a reasonable estimate of the average microenvironmental PM2.5 exposure that we experience. And so here's a pie chart just averaging across these scenarios, and it takes sort of mortality out of it a little bit and just looks at exposure. Where are we exposed to PM2.5, and where does that PM2.5 come from? And so the biggest one here, the biggest slice of the pie, is over a third of our total exposure to PM2.5 comes inside our homes, and the PM comes from outdoor origin. So that remains, by a slight margin in our models, the biggest exposure to total PM2.5. The next one we see is indoor origin PM2.5 exposed inside our homes, and that's another about 35% or so on average across our model scenarios. These are kind of our best estimates for the average across the U.S. housing stock. They may not be perfectly accurate because of a number of assumptions. The next slice of the pie is outdoor origin PM2.5 exposure that occurs inside other buildings like offices and restaurants and so forth, and that's around 11%, followed by indoor PM2.5 origin exposures inside other buildings, which is around 9%. And then finally, our average outdoor origin exposure is similar to what we saw earlier. It's just about 7% or so, because we don't spend that much time outdoors, even though when we are outdoors, we're exposed to 100% of the PM2.5 that's out there. And then vehicles, exposure to outdoor PM inside vehicles makes up the last little portion here. So I mentioned there's a lot of uncertainty here. One thing that we can do is try to get the ambient attribution right. And so basically what our model does is reassign ambient exposures based on all these microenvironmental exposures. And so we ought to be able to reasonably recreate mortality estimates associated with ambient PM2.5 sources, because we're just reallocating in the model where they're actually exposed to, but they should yield similar results to the outdoor only, or the studies that use outdoor concentrations as surrogates for exposures. And so I think we did a pretty good job of that. So if we look back to these five studies that estimated the U.S. mortality burden in various years associated with ambient PM2.5. Remember, we used 2012 data, so it's kind of right in the middle of these studies. Our best estimates range sort of 140 to 160,000 deaths associated with ambient PM2.5. Of course, most of that in homes, and a very small amount of that outdoors. And that actually lines up really well with the literature, which, if you remember before, I mentioned ranges from about 90,000 deaths to 200,000 deaths or so, some even higher than that. So we're right in the middle of that. So it sort of shows that at least the model can get the ambient attribution right, and then we can make the leap to kind of predict indoor origin exposures in these different microenvironments and what the magnitude of mortality burden to those exposures might be. But it's really quite impossible at this point to even verify that. And so speaking of that, there's a number of limitations to this work that are really important for us to highlight. And so some of these include of course, this assumes that there are causal and quantifiable relationships between mortality and ambient PM2.5 that exist from all of the decades of epidemiology literature. Parham mentioned we assume no threshold concentration, meaning there's no concentration below which there are no effects, but the model can handle that. And basically, if you do add a little bit of a threshold concentration, just the total magnitude of mortality decreases a bit, that's all. So far, we haven't considered other forms of exposure response functions. I showed a number of those forms, mathematical forms. That's something we could add in the future. So far, we've used kind of a generic health impact function, a sort of a traditional function. We did not consider the possibility of double counting of health effects that would be associated with indoor PM sources in prior epidemiology studies. The idea here being that, well, everyone, even in these outdoor ambient or these ambient epidemiology studies, there's inherently some indoor source exposure that has occurred there. And so are we double counting deaths or double counting mortality? There's a possibility for some of that. We think it's relatively low because we haven't seen a lot of good evidence that there's variability in indoor exposure among different regions or different types of populations, but we just have a lack of data there, I think. We've also seen a number of studies that show pretty low correlations between people's actual personal exposures and outdoor concentrations. There's variability there among different populations, but when you look at big summaries of those studies, they're pretty low. A couple other limitations is that, as Parham mentioned, we didn't consider any variability in PM2.5 toxicity or the effect estimate based on chemical constituents of either indoor or outdoor sources. Most of that's due to data limitations at this point, but could be done later. And we didn't consider any changes in toxicity that might occur due to the size-resolved particle dynamics. When particles transport from outdoors to indoors, they can undergo some changes based on indoor and outdoor temperature differences and stuff like that. And we have no idea if actually that mechanism or that transfer process changes toxicity for better or worse. We have no idea of that at this point. And then, of course, in our model, again, Parham mentioned, we assume equal toxicity or effect estimates for indoor and outdoor PM2.5 sources. That may not be the case. There's very limited literature. Some show it's a fine assumption, some show it's not a great assumption, but there's only about 4 or 5 studies that I've found in the literature that have tried to even document this. So it's a really kind of a missing piece, and there's some precedent for this assumption in a number of other studies. And so that leads us to really our last slide here, which is there are a number of ongoing research needs that we see from doing this work, and one of those is that we really don't have great nationally representative studies of both indoor and outdoor PM2.5 sources in the various microenvironments in which we spend our time. We've had to kind of cull this from the literature as best we can and make a number of assumptions. That's why you see these scenarios, and we don't actually know which one is the right one. I mentioned this just a minute ago. Ongoing research needs are we really don't have differential toxicity studies. So, for example, does ambient PM toxicity change as it infiltrates indoors? Or are indoor PM sources equally toxic or less toxic, more so? What does it depend upon than outdoor sources? We don't really know that. Like I mentioned, we could incorporate different exposure response model forms and model parameters in here. And we could also think about translating this to other PM metrics, whether it's PM1, particles less than 1 micron, or ultrafine particles, and maybe other health endpoints like short-term acute effects or other non-mortality effects. But those are just other things that we could see that could be done. And so with that, we're at the end of our time. Really want to thank EPA for allowing us to host this and for the number of supporters of our work, and for all of you who took time out of your day to listen to us. We've left our email and contact information here, and I think it's time to open up for questions if we have any. So thank you very much.
Thank you. We've received many questions, and we'll start with this one. This attendee asks, how are the indoor-outdoor measures distinguished in scientific studies? Is it the same across all studies?
Well, so I'll take that one. If you're talking about epidemiology studies, most of them have not accounted for indoor exposures to indoor or outdoor sources. If you're referring to kind of like the field measurement studies, like the RIOPA studies and the MESA air studies, they're tricky. Then we use those 2 studies because they're 2 of the really largest cohort measurement studies that we're aware of that measured indoor and outdoor samples, but also did some other analysis to try to estimate how much PM2.5 comes from indoors and how much comes from outdoors. One of them, the MESA air study, used sulfur as a tracer. There's been some good literature over the years, kind of in the early and mid-2000s, showing that there aren't that many indoor sources of sulfur, and there there does exist sulfur outdoors in outdoor PM 2.5 samples. So if you find it indoors, it's a reasonable surrogate for how much PM 2.5 came from outdoors. Although I know sulfur has been declining in ambient environments over the years, and this method may be kind of losing some utility from what I've seen in some conference presentations lately. And then the RIOPA study, which is a little bit older, used kind of like a number of mass balance and statistical models. So they kind of made assumptions for a variety of parameters that govern particle transport and persistence kind of processes. So it's a little like less sulfur, less experimental, more sort of a model in itself. And there's some uncertainties within that as well.
Thank you. Our next question, this attendee asks, given this large potential mortality from exposure to indoor PM 2.5, can you suggest what homeowners, renters, and residential HVAC contractors can do to reduce these risks, such as actions that would probably be within their control?
Sure, that's a great question. So I've actually got a couple of bonus slides here that I will skip to, in part because this provides a helpful link. So, I mean, fortunately for indoor air, in some ways indoor air is actually easier to control than outdoor air because you can just do things like buy filters and air cleaners. And so this is a summary slide of what we've seen, or of a few resources, basically. So there's been pretty good evidence from a number of studies that using particle air filters, HEPA filters, or close to it, with enough airflow that you get a lot of flow, through the device, and enough media that it lasts a long time and removes a lot of particles. Not every air cleaner does that. So if you want to learn more about that, I recently worked also with the EPA to help edit their new guidance on air cleaners and air filters in the home. And so you should visit this link here. There's like a consumer-friendly piece that's only a few pages that provides a lot of recommendations. Basically, central air handling, if you have forced air systems, if you install like a MERV 13 or higher, you can reduce PM 2.5 by a good amount. The only problem is a lot of our systems don't run that often because they only run to meet heating and cooling needs. So that can be kind of tricky. But then you can operate a portable air cleaner in the spaces where you spend most of your time, and if you operate it continuously, they don't use that much power. You can really make a big impact. And I'll also note that through these, there's been, I think we've reviewed about 20 studies that have done air cleaner interventions where they gave people air cleaners, measure their PM concentration reductions, and then also measured a number of health effects, sort of biomarkers of short-term and long-term health effects, and a few other things like that. They're all summarized in the technical summary. This is kind of the longer document as a piece of this EPA guidance. And basically the summary there is that on average what we saw is in the literature is that when you give people air cleaners, they tend to reduce PM concentrations, usually PM 2.5, by about half. So they can make a big impact. They can do better in some environments, worse in others for a couple different factors. As long as they're running, they can do well. And then there's actually a number of documented health improvements in these like biomarkers that have been measured and other things like allergy and asthma symptoms. So there's been some modest improvements in lung function. People go to the doctor for asthma when they have asthma less often, and there's been these kind of small improvements in markers of cardiovascular and pulmonary health. Very few studies have looked at central filtration, but the portable air cleaning studies are somewhat convincing that not only do they reduce PM indoors, but they also improve some marker of health effects, which is another way of kind of us learning that indoor sources probably can also have an effect on health as well.
Thank you. Our next question, can you clarify the difference between indoor-outdoor ratio and infiltration factor?
Sure, happy to. And sorry if I got lost early on. The long and short is infiltration factor just tells us how much of indoor PM comes from outdoors. So it's a number that's capped between 0 and 1. If your building has an infiltration, or your vehicle or whatever environment has an infiltration factor of 1, it means that 100% of the PM that's outdoors comes in and persists indoors. In a home, really the only way you get one is if all a couple windows or all the windows are open, and you might get close to one. Indoor equals outdoors. If your home is zero, or if your microenvironment is zero, that means that you actually don't have any exposures to the ambient pollutant at that point. And so here's just some data from the literature shown here on ranges of infiltration factors across homes and across cities and across seasons. It varies a lot. Indoor-outdoor ratios are like the infiltration factor plus whatever's emitted indoors. And so it gives you some unknown mixture. It says, well, indoors versus outdoors, indoors being a function of outdoors plus indoors, and that's all we know about that.
Thank you. We have another question. This attendee asks, does life expectancy change with the age that a person is exposed to PM?
So I think what I hear is, does the exposure window matter? I think that's what I'm hearing.
Yeah.
Yeah. That's a good question. I'm not. You tend to see higher impacts, I believe, in most of the epidemiology literature on older populations. So to that extent, I think you can sort of say yes to that. But I would have to. I don't know studies that have looked like that clearly at certain exposure windows. I think it's more the epidemiology has been mostly more sort of exposures concurrently at the sort of time of study or over a long period of time. So it's a good question. I'm probably not the most qualified person to answer. There's probably some epidemiologists out there that know more about that. I can't think off the top of my head, though, of specific studies there.
Thank you. The next attendee asks, how does this study consider the effect of other contaminants of concern, aside from just particulate matter, on mortality?
Yeah, that's a great question. So we don't really actually, we personally have not taken that into account, these sort of co-exposures or co-pollutant exposures. And my understanding of the epidemiology literature is that many of the studies using ambient monitoring or ambient pollutant monitoring have taken into account, sort of multiple pollutant exposures, but not all of them. But they do that in part because we measure, ozone and SO2 and NO2 and a few other things for regulatory purposes. So we have that data, and you can kind of control in the models for ozone acting alone, particles acting alone, and ozone and particles acting together, and that sort of thing. There are fewer of those studies than there are the kind of just looking at PM 2.5, so it's a really good question. I can't think of a great survey of that literature, like an overview of that literature, but generally we tend to see PM 2.5 coming out with either the strongest signal or one of the strongest signals in like co-pollutant models, basically. It's a really nice question, and we don't really address that at this point. We take the relative risks associated with PM 2.5 from epidemiology studies, many of which have controlled for co-pollutants, but not all. So we kind of assume that that's taken care of, but it's another uncertainty.
Thank you. Our next question comes from an attendee who asks, this work was clearly focused on residences, but it prompts another question. Are there implications of your work for federal workplaces? For example, courthouses, offices, military barracks, United States embassies in other countries, etc.?
Yeah, that's a good question. So what I'll go back to here, since it's not far away, is that, yeah, in terms of ambient exposures, or what we'll say is indoor exposures to ambient particles, the second largest ambient exposure after homes was actually inside other buildings, like the buildings you're talking about, where we spend 8 hours a day, 5 days a week for the working world. And then right behind that was indoor exposures in other buildings. So that's about 20% because we spend a lot of time in these types of buildings, and more so for some others, for some parts of the population. So the sort of net issue there is that we have a lot of uncertainty in that estimate. There aren't great existing studies like there are for homes that we mentioned that have teased out the relative importance of indoor and outdoor sources inside offices. Offices are more complex in some ways, more complex systems. Indoor sources are, they're bigger volumes, and indoor sources might be concentrated in some areas differently than others, around copiers and things like that. So that was actually kind of a weak point that we noticed as another limitation in this study, that we ended up to make estimates of our indoor exposures in office-type buildings and other types of buildings. We relied on a study that was really looking at indoor exposures of indoor origin in those types of buildings in Finland. And we kind of had to make the assumption that those are reasonably consistent. There just haven't been many comprehensive studies that have looked at the average and distributions of indoor sources inside offices and places like that. So basically what I would say is, to answer the question, is that you're something like 20% of total PM 2.5 burden on average across the population occurs in these other types of buildings. So they're probably important, but we could also improve our estimates a little bit if we had a little bit better data.
Thank you. Our next question. This attendee asks, what are significant sources of indoor particles?
Sure. So indoor particles, some of the big sources are in homes, cooking, homes and restaurants, of course. Cooking, that's from both gas stoves and electric stoves, because you get particles emitted both from cooking the food itself and also from the heating source, combustion for gas stoves, and then just heating elements for electric stoves. Candles and incense are big, intentional sort of sources. Cleaning activities are really big sources, like dusting and vacuuming and ironing. So sort of the great irony there is while cleaning, you're generating exposures quite often. Tobacco smoke, it can be an overwhelming source in a lot of in homes or in buildings where there is smoking, but not in others. And of course, there's a bunch of appliances like photocopiers, laser printers, 3D printers, and that sort of thing. And then, of course, another big source indoors is actually outdoor particles. There are other sources, and the thing is, indoors they're varied, they're intermittent, they vary in terms of composition, they vary over time, and then they vary in the size that's emitted as well. A lot of sources are actually ultrafine or very small particles in indoor environments.
Thank you, Brent. I believe that was our last question of this webinar. So I'll pass it over to Allison Clune for any last words.
Thank you, Christina, and thank you, Brent and Parham, for that excellent presentation.